Cool. Okay, so today I'm going to talk about, there's not going to be much algebra, but maybe at the end there will be. And basically we're going to talk today about something that it's called quantum homological codes. Codes. So this is something that has to do with codes, which is something in computer science or in information theory. But it relates to, it actually has a very strong relation to what we do here. My main goal here is just to show you how from codes we get to stuff that have to do with lattices and Lie groups, and that there's a very strong relation. So basically what we'll do, we'll start by talking about what are codes, and that will be a main part of the lecture because we're not assuming any knowledge in that. And we'll see how codes, the problem of codes can be translated to something, to more combinatorial problem, such as graphs and complexes. And from there, we'll try to translate this into a geometrical problem, which has to do with manifolds and locally symmetric spaces. And if you know it's locally symmetric spaces, so you won't be surprised that from here we'll make it somehow to algebra, theory of lattices, Lie groups.
Maybe switch if you want to.
Yeah, there was a good that one. Yeah, this is good. Okay. And once we got here, so I don't think we'll have time to talk about it, but even from here there's another little thing that is, in some sense, goes even to number theory. And this relates to something called arithmetic groups, which is a certain kind of a lattice. And actually, in many cases, it's exactly all lattices are arithmetic groups. So this is already, we might even make it until there, but the point here is just to more make those, to see how this translates more than actually establishing theorems in those fields that we're doing usually. Cool? And because it's not such a standard lecture here and this, so if it really asks a lot of questions, I think it's harder to prepare this kind of lecture than just starting with this field, so go ahead and ask a lot of questions. Okay. So what is a code, first of all, okay? So in general, codes are concerned in how to represent information in different ways, okay? And a particular kind of interesting code are error correcting codes. So what are error correcting codes? Suppose I want to send a message to someone else, but there's a chance that there'll be interference because it's a noisy channel, or even when you talk on the phone, sometimes someone doesn't hear you. So you want to kind of encode it with more data in such a way that even if there'll be some errors, the person we're sending it to could recover it. So let's take a very simple example. We have Alice, we have Bob. And Alice wants to send Bob one bit of information. It could be either 0 or 1. And it passes, but then let's say there's I don't know, a 10% chance of a bit flip. That means that the 0 will turn into a 1 or a 1 into a 0. So Alice, instead of sending 0, 1, she'll first encode the data in a larger space. It will first do an encoding, we'll call this F, and we'll encode 0 to 0, 0, 0, 1 to 1, 1, 1. Okay? Now there's still a 10% chance for every bit to flip. But the chances, assuming that at most one, let's say, I don't know, something flipped here, or if 1 was sent, so something flipped here, but then Bob can recover the data with something called majority vote, meaning Bob will just check if most are zeros, then it's probably a 0. Okay? So this is an example of a code that can correct one error. Okay? And so this brings us to to important the notions of a code. So this is a type of what's called a 313 code. Okay? Why? So this is, in general, we have NKD. N is called the length of the code. This is how many. So basically a code is a map from Z2, this is a classical code, not a quantum code, from Z2 to the power of K into an embedding inside Z2 to the power of N. We want to encode K bits, and we use more bits, N bits, in order for the information to be protected. So N is called the length of the code, and this is N. And these we call these number of physical bits. Because physically Alice sent about 3 bits of information. K is called the dimension of the code. This is number of logical bits. And D, the minimal. So first of all, the image of F inside the range, this is called the code. So when we say the code, we mean a set of elements inside a big space that these are the words, because this is not a word in the code. The only words in the code are 0, 0, 0, 1, 1, 1. These are errors, which we correct back to words in the code. D is the minimal distance between words in the code. Now we need a metric, but the natural metric on this space. So if we have a word inside this, the norm of this word is just the number of coordinates, however you spell it, which are 1. So this gives us a distance. For example, the distance between this word and this word is 1, because it differs in 1 bit. Very natural metric. Okay?
So this map, if you're considering it to be a linear map?
Not yet, but yeah, very soon, yeah. It could be any map. So why is this a 313 code? We encoded 1 bit of information. Inside, in order to do that, we used 3 bits. And the distance, we have 2 words. The distance between these 2 words is 3. So what we really did is let's say in general, we have many words, possible messages that we want to send in a small space. We take a bigger space and we make them farther apart from each other. And now, even if this will do an error, we could still see where the closest place that it should be, and that's how we correct it. So the distance, so N tells you how many bits you use, K is how many bits you actually encoded, and D in the end tells you how many errors can it correct. And a very almost trivial claim is, this is not good either. Okay, let's try. This is yes. Okay, claim. Oh, good. A code with distance D can correct D, and we round it down, errors. So the intuition is clear. If the distance between every word and every other word is D, so we can tolerate, as long as this error has accidentally this moved to here, we're still okay, because when we'll move it back to the right place. But if it passed already more than D over 2 distance, it will pass here. So we sent this message, but Bob will think that it was here and there was an error to here, so it will correct it to here.
Here, error means bit flip. Single
Yeah,
bit flip.
yeah. This is Each error is a bit which was flipped. So in our case, the distance is 3, which means what is 3 over 2 is 1.5, but we always round it down, so it's 1. This is a code that can correct 1 error. If we have 2 errors, then we're screwed.
So, just d over 2 dash errors. It's not the number of errors, it's the type of the errors, right? It's
What do you mean?
errors of size.
Yes, okay.
I'm just
Can correct. We can think that each error is anything, and then it's like the support of the error, or something like that. Yeah.
Okay.
Basically, we think of each bit as if we pass one by one, for instance, and each one can have an error. Okay, is it clear so far? Okay. And okay. So now, in general, like in everything, like in computer science, we won't consider just one code. We'll always consider a family of codes, because today we want to just send 10 bits of information. Tomorrow we will want to send 100 bits of information, and the next day 1,000. So we want actually a family of codes with increasing parameters. Okay. So a natural way to, let's say you're not so satisfied with this code because 2 errors and you're screwed. So we can do a different code. 0 will go to 0, 0, 0, 0, and 1 goes to 1, 1, 1, 1. And this is n times. Okay? So let's try and think what's the parameters of this code. So n is just n. We used n bits. How many bits are we encoding?
2.
1. No, still 1. We didn't improve that. We're still just encoding this one. And what's the distance? N, exactly. The distance between this word and this word is n. So we improved the distance of the code by adding more bits, but the dimension stayed 1, okay? And this is a family of codes. We call this Cn. And we'll be interested in 2 other parameters. One is called the rate, which is k over d, k over n. And the relative distance, d over n. And this is just because we want to kind of normalize it in n. We understand the asymptotics of the code. So in this case, the rate is terrible. It tends to 0. 1 over n tends to 0. We use more and more bits, and we still just encode 1 bit of information. This, however, goes to 1. So this is an example of code with a terrific distance and a terrible, it's actually a family code, but with a terrible rate, which is, we still encode always 1 bit of information. Okay? And so in general, what do we call good codes? Okay? So as I said, the rate of this code is terrible. So what do we expect from a code? When will we say that a code is good? Of course, could change, depends on your needs, but at least for here, we say a code is good if it has linear, if it has distance, if d and k are linear with respect to n. Okay? So in this case, the distance is linear, but the k is not linear. So this is not a good code. Okay? And there's another property of codes that we call, I'm not going to go into it, but just for this, I'll just state it. So this is a fact or a theorem. There exists good and even very good, I'm writing LDPC, it's another property, a good property, codes. Okay, this was proved first by Gallinger. And it was just by random considerations. So you can, in some way you randomize a code, you show that the probability of it to be a good code is positive, and you conclude that there exists such a code. But then there was an explicit construction by Sipser and Spielmann. We use something called expander graphs, or expander codes. And this is an explicit construction of this, okay? Yes.
We're using
NKD to say that what's a good code or like what's a, if you're talking computer science, maybe it's a low complexity or not a lot of space. But we're not thinking about the function itself. It may be very complex and not efficient to compute the function itself.
You're right. There are other aspects that are very important, which is called the encoding and the decoding. What Alice does, she encodes the bit into a bigger space. What Bob does is decoding. A lot of it's a very good question of whether you have a good decoding algorithm or not. Sometimes you don't have a good decoding algorithm, and that's still, you can say it's not a real good code. In this case, they are.
So you're saying good code also with respect to decoding and encoding.
Well, for now we don't. This is like the next, because we're going to talk about in quantum codes. We're not even asking that for now. So okay, so here's the major open problem. One of the most important problems in quantum information now. Does there exist good quantum codes? Now we didn't define yet what's a quantum code, and we'll talk about it soon, but it's just an analog of this to the quantum setting. And I'll do LDPC. And this is an open problem, and this is the main, this is what leads us to this lecture.
Let me interrupt just and say, since we are in a group theory with Rashal here, this notion of expander codes coming from expander graphs, which you may be familiar from computer science, but you also may be familiar from group theory. The way to construct such is using groups and which have property called property tau or property t. And I think we should devote some lectures to study property t here, and so we have volunteers for this. Please approach me.
To construct good codes?
No, not to construct. It could be used to construct good codes.
So just one uses
I'll talk about
a
it.
group theoretical
For now, it's
property
just a
called
good
property
property.
t in order to
Codes,
produce expander graphs. And this is what these people
Low density
do.
parity check.
Okay.
And that will explain.
Okay, is it clear? Because this is the basic, and at this point it should be completely clear everything. So if not, we should.
Can I ask you something very specific? If you take a word and duplicate it, is it a good code? Because it seems like k is half of n and d is maybe quarter or something.
If you just duplicate, you want to kind of generalize this, but
No,
instead
just
of
to
just
find an example for a good code.
So R is 1/2, right?
Yes.
But what is delta?
Maybe 1/4. I don't know.
No, here delta is terrific. R is terrible.
No. I mean,
Yeah.
if you take
You
a
want an
word-
example of a good code?
Yes.
It's hard. You need an well. It's a big theorem. I mean, we need to show constructions of expander graphs and how you can define codes on them that will.
Okay,
give
but-
you good codes.
D would be 0 because you might have a word which is a double of the other given word.
The
proof.
You get all possible
The proof of showing that there exists a good code is not that hard. You just have to draw a matrix and then show that the distance between balls is with positive probability that it's good.
Yeah. So this is the first proof.
The first proof
The
is
first
pretty
proof is
easy.
given. Okay. I never saw it, but yeah.
If I remember correctly.
So these codes are also easily decodable?
no.
I think they are. I'm very glad there are no computer science people. I brought physics people here, but I'm very happy there are no computer science people here. Okay, I'm not too familiar with code theory.
Wait. Sorry, I still didn't quite understand. You take n to infinity. It means that for every n, you define another code. Like a code is a series of
It's a series of
such
codes.
definitions.
Yeah, as you see
Okay.
here,
Yes.
this is n. So it's always
And
we
k
say code, but we actually always talk about family of codes because you want
Okay,
to talk about
yeah.
the asymptotics. It doesn't
and
help
k, so k also changed. The language that you code also changed.
K
Yes.
is a function. K is a function of n,
Okay.
and d is a function of n. And then you ask how this goes when n goes to infinity.
Okay.
Okay, good. Okay, next we're gonna talk about linear codes. Okay. So definition. A code. So we can can write it, usually in code we talk only about the image of f, but let's write it really explicitly. It's called linear if f is linear. Okay? This is a good setting to work with. It doesn't really restrict much the codes that you can construct, and it's clear why it's simpler to handle those kind of stuff. For example, claim let C be a linear code. So if before the distance we had to check between any two words in the code, there could be many words, and check the distance between them and take the minimal one. So here it's enough just to take the word, the non-trivial word of lowest norm. Okay, so D will be equal to the norm of W out of all W in the code, which are not 0. Because there's a nice structure here to, will look, for example, something like this. So the distance here will be the same as the distance here. We can always shift it back to 0. So it's already a nice, it's much more symmetric when we talk about linear codes. Okay? So this will be the setting that we'll always talk about. And now we're going to show a very nice, even a more basic, inside linear codes, there's a family called homological codes. Okay? And what are homological codes? Okay? So the idea, I'll state the theorem and then show how it makes sense. Okay? Let G a finite graph.
So D is the minimum over all these categories?
Yeah. Okay, so let G be a finite graph. We can assume it's nicer and connected and stuff, but it doesn't really matter. So we start with a graph. Then there exists a code, a NKD code. That's the parameters of the code. We'll call it C of G, where N is the amount of edges in the graph. K is the amount of basic cycles of the graph. So one way, I'll explain it soon, and one way of formulating it, it's the dimension of the first homology group, which is the only interesting homology group in a graph, which is also 1 minus the Euler characteristic of the graph, where Euler characteristic is the number of vertices minus the number of edges, which basically it's just the amount, just cycles, but basic cycles, because you can construct bigger and bigger cycles. Okay, I'll show how we do this construction, and it will be very intuitive. Okay, it's really not difficult. Okay.
Is that the assertion of the theorem that there exists a code?
Yes.
Is that the assertion of the theorem that there is?
Yeah. Let's G a graph. Yeah, it's more construction than a theorem. Yeah. Okay. So let's just start with a graph.
What about D?
Well, yeah. D, the girth. What is the girth? Length of smallest cycle. Okay? We'll see in a second. Okay, this is a graph. This defines a code. Okay, let's see how this happens. We already said that n will be equal to the number of edges. So we're really inside our physical space will be z2 to the power of n, which is, so what we think of it is that what Allison's bub is, for each edge on the graph there's a bit, and this bit can be either 0 or 1. So for each edge corresponds a bit, and we think that whenever the state of the bit is 1, then we mark this, we can do it with a different one, then we mark this edge, and whenever it's 0, we don't mark this edge. Okay? So this makes sense. Now it makes sense to say what is a word which is a cycle. For example, this is a cycle, and formally this is a word which has 1, 1, 1, 1, 0, 0, etc. Clear? Yeah?
No,
Okay. So to
So
each.
you also number the edges before.
Yeah, I don't have the order correct. It's just, the point is that this is there'll be 4 ones correspond. So to each edge, we have a special bit. That this bit says, is this edge on or off? Think about it that way, okay? And a cycle is just we draw this. For each subgraph here, you choose a bunch of edges. Will be a corresponding word. What is the word? The word where for each edge which is in that subgraph there'll be 1. For each edge that is not in that subgraph there'll be 0. You can call it like the characteristic word of that subgraph.
Each you have a sequence of possible zeros and ones, and the order of them is fixed. Kind of.
Yeah, the order is fixed. So we really think of this as z2 to the power of e. Yeah, it's
Yeah, so Alice and Bob decide to begin with how to
Yeah.
order the edges.
Yeah.
Give index to everything.
Okay, so the words are corresponding to subgraphs.
the words are in full correspondence with subgraphs. A choice of edges. The edges that will be 1. You choose which each given a word. You color all the edges which have the label 1. We can even just, there's no meaning of writing it like this. We can actually write 1, 1, 1, 1, 0, 0, 0. Suppose this is what Alice sends Bob. Okay? Now, this is a cycle. Also, this is a cycle. Now, it's not hard to see that the set of cycles, which is a subset of this, so let's call the set of cycles, just write cycles. This is a linear subspace. Because if you take this loop, which is just 1, 1, 1, 1, 0, 0, 0, 0, plus this loop, 1, 1, 1, 1, 1, 0, 0, 0, 0, because we're working over Z2, so this cancels out and we get this big loop. So a loop plus a loop is another loop. Okay? So this is a linear, so formally this is a linear code because we're working inside Z2 to the power n, and we chose a linear subspace and we call that the code. Okay? And, okay, so let's see why these parameters. So n is equals the number of edges, this is clear. K is equal just the number of basic cycles, because that's the basis. We want to ask how big is this subspace. It's the dimension of the subspace, which is just how many, it will be in this case, 1, 2, 3. And then you can of course have all the linear combinations of those 3. It's just the first homology group, or whatever you're more comfortable with. This is also true. A way to see it, by the way, is just choose a spanning tree. A spanning tree for the graph. Well, I don't want to get into it. Okay, it will be too long. Okay. And why is
But
the
basically did it last time.
True, yeah, that's true. Yeah. And why is d the girth? Because let's say that here, in this case, the girth is 4. The minimal cycle is of length 4. So if we, let's say there were 3 errors. So we sent this to Bob, and this got from 1 to 0, and this got from 1 to 0 accidentally, and this got from 1 to 0. Bob will now think that this loop is not on. Bob will think it's off, because Bob will do a majority vote. Okay? Or maybe accidentally this will turn on and this will turn on, and then Bob will not be sure whether there is that loop or there isn't that loop. This is why the distance is exactly the length of the minimal cycle.
It's just pretty much the claim you said before.
Hmm?
The claim that you wrote above, since it's linear.
Okay, what are you saying?
This.
The claim
Because
that
it's
you
linear,
Yeah.
the distance is the minimum of the minimal
It's
level.
true,
Which is the minimal.
which is just, that's true. In this case, the code is the set of cycles. So we take the cycle of minimal length. Of course, you have the trivial cycle that we don't count, which is all zeros. That's also a cycle. We think of it as a cycle, okay? Now, even if you're not completely clear all of this, all what is important at this point is to understand that we reduced a problem of finding codes to the following problem. Find graphs which have a lot of loops, but that loops should be big. If you have one small loop, then there is a chance that there will be an error that we won't be able to recover. So here we translated a problem from codes into a purely combinatorial problem. Okay?
You want both of them to be O shell n.
Yeah, so what we actually do is take family of graphs with more and more vertices, more and more edges, and we want that as we grow, it's very easy to make just more and more edges, but we want that the cycles, there will be more and more cycles on the way, and the cycles will grow bigger and bigger on the way. So it's a hard problem. Okay, so let's just show an example. And so here's a surprise. And the first code we defined, 0 goes to 0, 0, 0, 1 goes to 1, 1, 1, is a homological code. It comes from a graph. Which graph? This graph. This is a graph. The amount of edges are 3, so n equals 3, which is the number of edges. K equals number of cycles, which is 1. And D is the girth.
For next time you lecture the Midrashah, that should be an exercise.
Okay. Yeah. Well, then maybe the next one will be
The
an
next one,
exercise,
yes.
okay?
The one denoted CN, that's kind of...
Exactly. No, yeah.
That's kind of a hint, no?
Yeah, okay. So D is the girth, which is 3. So this is the code generated by this. Exercise. What about 0 goes to 0, 0, 0, the generalization of this one? Is this also a homological code?
Okay.
Yeah? Okay, what is the graph? Okay, just a bigger loop. Okay? Okay, good. And we can see that this is it's a nice graph because it has a very big cycle, but it has only one cycle, so it's not a good code, right? And but here's another way of generalizing the first one. Now that when we think about it as graphs and not as codes, and we have it in a different way we think of it in a different way, we can think of different ways of generalizing this first code. Because what is this graph? This is one way of thinking of it as the 3 cycle, but you can also think of it as the 3 click. This is a graph with 3 vertices, where every 2 vertices are connected by an edge. Okay? This is called, let's do K3. Let's take Kn, or Ks. Let's do the number of vertices. S is the number of vertices. So 1, let's do just 5. 1, 2, 3, 4, whatever. Okay, I know. Okay? This is also a graph, so it gives you a code. Okay, exercise. What are the parameters of this code? We have S vertices. How many edges do we have in this graph? S choose 2. For every pair of vertices, we have an edge. Okay? How many cycles? So we have a formula. It's 1 minus chi, which is the characteristic, which is 1 minus v plus e. So it's 1 minus s plus s choose 2. This is k, this is n. What's the distance of this graph? Of this code? 3. Here's an example of a very good, a graph, a family of codes, because S we can let it grow, of very good rate, but terrible distance. Because delta, the relative distance, which is d over n, tends to 0 now. K actually is linear. So this is complete, like in a way, opposite of the code. It's a different way of generalizing this this code in a way that will get very good rate but very bad distance.
You mean say R, not K?
Well, yeah, no. K goes
goes to 1.
Okay, K goes linearly by n, which means that R, which is K over n, tends to a constant which is bigger than 0. Okay?
Which is 1.
In this case, it's 1, but it could be something else. Yeah. Okay. And just about the question before, I said something, the word LDPC codes, because I mentioned that there are good classical codes, but there are good LDPC classical codes. LDPC means basically, because let's say now we send this to Bob, and Bob wants to check, to do this decoding thing. In order to realize whether we're inside the code or not, meaning that whether this is not in the code, because it's not a cycle, but let's say this is in the code, this is an okay word. In order to check this, all we need to do is to go vertex by vertex and count how many edges are 1. If it's always an even number, you know that you're a bunch of cycles. Okay? If you have one odd number, like here, this is an odd, you know it's not a cycle. Now, this code is an LDPC code because for each vertex, we just do one check, and each vertex one check.
The one to come with this local criterion is Euler. The one who came up with this local criterion for checking whether something is a code is Euler, right?
I don't know. It's elementary, but yeah, maybe it wasn't.
What is elementary?
What?
Yeah.
This is an example of so LDPC is it's not a property of a particular code. It's of a family of codes. It means that even when the code grows more and more, still Bob needs to do only local checks. But here, because the degree of the vertex grows as S grows, this is an example of a code which is not LDPC. Here, no matter how we let this grow, always the degree will be 2, so there'll be still, it's controllable the amount of checks that we need to do. Okay?
What is Bob checking?
Huh?
What is Bob checking?
Bob. What is Bob checking? Well, Bob first needs, let's say one question that Bob can see is whether the word is in the code or not. This is something I need to get into. The LDPC is a short for low density parity check. And so in order to really explain it, we need to explain what's parity check. And basically what Bob is doing is a parity check. It's a bunch of functionals on the linear space, or orthogonal, or a basis for the orthogonal complement of the space. And each one tells you, that gives you all the information about where you are and how do you correct your error. So it's just a decoding process.
Basis for the dual?
Yeah, a basis for the orthogonal complement of the space. Well, we're in a vector space. It's almost well defined because we're in characteristic 2. You don't really have a good inner product, but you can still define an inner product in the ordinary way, and you can say what is an orthogonal vector. So for each code, C, we have the dual code C orthogonal, and that's just the opposite code, and you can translate parameters from here to parameters here to here.
So just to be clear, Bob gets a message which is the green shape over there, the orange shape over there, and this is something in dimension S choose 2, quadratic in S. But he needs to perform only S checks, which is square root of n, in order to know that this is not a cycle.
Yeah.
This is just checking the
You're talking about this case?
Yes.
So square root of n is still not good. In LDPC we want constant.
Okay.
Yeah, so in this case, this is good and this is still not LDPC, but it's not terrible, but yeah, it's, good.
But here this is correct, right? The amount of checks that you need to do is of the order of square root of n.
I think so, I mean, if you see it, if you counted it, yeah. And Okay. Now, well, basically this was only for you to believe me when I'll announce the following theorem, which is, I think if I would start with it, then it would seem completely nonsense, but now I think you can believe when I tell you the next thing. I didn't define yet what's a quantum code, and I'm not sure I'm going to define it. That will depend on whether we'll see where we go, but I'll still, it's very, there's a direct analogy. Okay, so we still have NKD, same parameters, same process, it's just a different setting. So, theorem, quantum homological codes. Okay, so here we don't use graphs. We need, it's a bit harder to generate quantum codes for all kind of reasons. So we're not going to use a graph. We need also the faces of the graph. We need one level higher. So let's K, V, E, and faces. This is called a 2 complex, a simplicial 2 complex.
Simplicial or cell complex?
In
this
it's
example,
a,
it's a cell complex.
Yes, it's a cell complex. It's because yeah, it doesn't have to be triangles. I mean, but it's still true for simplistic complex and doesn't really restrict the generality. So I'm going to state it this way. Okay, let K be a simplicial 2 complex, finite, of course. Then there exists a NKD, and I do 2 brackets, and this is a convention when we talk about quantum codes. Okay, we just do 2 brackets to make it clear. NKD quantum code, where n is the number of edges, k is still the dimension of the first homology group. Okay? The only difference is if there is this face here, this is not considered as a loop anymore because it's contractible. This, if we don't have this face here, this is considered as, it's not a contractible loop, so this contributes to the homology group. Okay? Basically how many non-contractible cycles or a basis for it. And D, so in this case it won't be only the girth, we'll consider both cycles, and each graph has a dual graph, which is taking the faces to be the vertices. And that gives you also a graph, so we can talk about co-cycles, cycles in the dual graph. Okay? So D will be the, we call it systole. Systole is just, you'll see, think of it just as a girth for now. The minimum between the systole and the co-systole. If it's not completely clear to you right now what exactly this means, it's okay. Yeah.
What is F in this section?
Do you know what's a simplicial complex?
I get it, like, is it yeah, basically.
So F is the next level. This is vertices, this is edges, and this is triangles. It's, yeah.
Why is it called quantum? Why quantum?
Why is it called quantum?
Just 2 words.
Why not what?
Well, like, I don't know, I don't see like what, see why you should go.
Okay, so there is a formalism of called quantum computation. Just like you have a Turing machine in classical computation, you have quantum machines which are analogous, and then you have a whole formalism of how this works. So just like when I showed you it's a classical code, it's clear that you can do it in, that this is something very realistic. In the quantum setting, you just have a new definition for what is a code, which goes well with the formalism of quantum mechanics. That's really a quantum. I mean, this is actually goes with the formalism. It's not just a name. This is just in quantum communication, or if you think of what is quantum information, you'll have a bit analogous definitions of exactly. For example, n will be a dimension of a Hilbert space. K will be a dimension of another Hilbert space, which is embedded in that Hilbert space. It's just a different formalism.
So instead of using Z2 to the power K, you're going to use some other vector space.
Exactly. So it's Z2 is a discrete. We're going to use something continuous.
So actually, it would be nice to hear about it. Maybe
Okay,
not today,
so,
but at some
great.
point.
So I'm very glad that I got it. This is exactly the point I wanted to get in the break, and it's exactly the time. And I wanted that on the break, you'll decide whether there are 2 options from now. Either I go already straight to to the geometry, into the algebra, and etc. Or before, anyways, I think we'll get to it, but before we can take like another extra 10-15 minutes where we'll introduce basic of, first of all, what is quantum information. You don't need to know any physics for that. And what is a quantum code, and kind of give a proof for this, which will make sense. So think about it in the break, and just before that, before we do that, I just want to generalize this theorem. And if you believe this, you'll definitely believe the generalization of the theorem because it's very natural. So why take a too complex? Why only two-dimensional things? Okay, let's take any dimension. Okay, so we have vertices, edges, triangles, three cells until D. And why encode everything? Why each edge should have a bit? Why not each face should have a bit? Or each vertex, or each something of higher dimension? So this is a simplicial D complex. And for any I from 1 to D, there exists a NKD quantum code. Let's call it CI. This is the ith code, where N is not the number of edges, but the number of I cells. This won't be the first homology group, it will be the ith homology group. And this won't be the systole, it will be the I systole and the I cosystole, which basically means that it's not the shortest loop, but let's say the two systole, it's the shortest non-contractible sphere, or shortest, you just generalize it to higher dimensions, okay? And this is nice. One more thing before we go out, I want to give just an example, something called the Torah code. And this construction was way before they had this formalism for homological codes, and it was much more an explicit construction. So let's consider a torus, but we're talking about complexes, so let's think of it as just this grid. It's a finite grid, and we identify the left to right and top to bottom in order to obtain a torus. Okay? And let's say this is an n over n grid. So from this theorem we get a code. What is the code? What is n? N is equal to the number of edges. Okay? How many edges there are here? So
I is 2 here.
I equals 1 here.
I is 1.
We encode, I1 means that the data is encoded in loops, not in spheres or in higher dimensions, okay? So 2n squared, the homology group of the torus is the size of it is this 2. We have 2 non-contractible loops. Of course this generates a four-dimensional vector space over Z2, and the distance will be n. Okay? So this is the Torah code, and we see that this is, of course, n, we can make it larger. This is an example of code which has bad distance, terrible, bad rate, terrible, and also not such a good, this is square root of this, even not such a good this, but still this was a, this major open problem is we're very far from solving it. So even this code was a very nice achievement. Okay? Okay, break.